Hi guys, it's Kate, and this is the topic review of questions on practice exams and old final exams about second-order differential equations. Before we get started and jumping right into these questions, let's remind ourselves what this topic is all about. Second-order homogeneous differential equations with constant coefficients is technically what their name is. Second order meaning that the second derivative is involved. Homogeneous, meaning that 0 is on one side of the equation. And then constant coefficients just refer to the coefficients on the first derivative, x prime, and the function itself, x. And so when we first started looking at differential equations that are of this particular form, one of the things that jumped out at us was that there must be a really close relationship between the function, its first derivative, and its second derivative in order for some sum of multiples of those functions to be equal to 0. That the first derivative, the second derivative, and the function itself need to really resemble each other in some way in order for their sum to be 0. And of course, our hunch was that exponential functions were involved. These are a family of functions that are defined by how closely their derivative is related to the original function. Now, following up on that hunch, if we took some sort of general exponential function, c times e to the rt, then our first derivative becomes r times c times e to the rt. Note that c and r are just constants here. And then our second derivative becomes r squared times c times e to the rt. When we actually see under what circumstances a function of this particular form would satisfy a differential equation like this, we go ahead and plug in our x, x prime, and x double prime into our original differential equation, and we get that c and r would have to be chosen accordingly. We note that c times e to the rt is a common factor, and I should say big C. This one is a little c right here. This is a big C, our constant. And so we should factor it out. And we're left with the fact that we need to choose r and big C so that the following holds. That we have that big C times e to the rt times r squared plus br plus c equals 0. Now, unfortunately for big C's got nothing to do with making this equal to 0. And why is that? Well, trivially speaking, the only way that big C times e to the rt could be equal to 0, because we know that one of these terms in this product have to be equal to 0 in order for their product to be equal to 0. The only way for this to be equal to 0 would have to be c being equal to 0, which means that x is just the 0 function, and so x prime is 0 and x double prime is 0, and yeah, that does satisfy this differential equation. But obviously we're looking for c to be a non-zero coefficient on e to the rt, hence all the work going into this. Well, this is never going to be 0. Exponential functions are never 0. The only place where 0 could possibly come up is in this little term right here, r squared plus br plus c, known as the characteristic equation. And so the characteristic equation and a hunt for its roots is the central idea behind solving these types of differential equations. We want to know under what circumstances will this whole thing be equal to 0. And so asking what the roots are of the characteristic equation becomes our new significant question. Now, our characteristic equation can be arrived at just by looking at the second order differential equation. We see that the coefficient on r squared right here is the same as the coefficient on x double prime. We see that the coefficient on r is the same as the coefficient on x prime. And we see that the coefficient on 1 is the same as the coefficient on x. And so we're looking for what the roots are of this characteristic equation in order for us to solve this differential equation. And just like any quadratic equation, there are 3 possible scenarios. One is that we have 2 real roots. Another scenario would be where we have 1 repeated root. And the final scenario would be where we have 2 complex roots. Knowing what to do in each of these three scenarios is absolutely critical to being able to answer questions about this topic fully. You should know the general solution for x as a function of time in each of these cases. You should be comfortable with each of these three types of general solutions, where they come from, why they make sense, and how to use them in tandem with initial conditions to solve for a particular solution for a differential equation. Our first day of this 3-day unit, we discussed the outcome where there are two real roots. On the homework, we looked into the case where there's one repeated root, and you use substitution to derive this as the general solution. And then for the 2 days, both day 2 and day 3 of this unit, we worked in the complex situation. We used Euler's formula to translate it into this format, which makes much more sense and makes life so much easier. And last but not least, you should be aware that this second order homogeneous differential equation with constant coefficients can occasionally model the motion of a spring. Under what conditions does that happen? Well, B, the coefficient on velocity, needs to be greater than or equal to 0. This is friction. If it's 0, that would be a frictionless situation. And if it's positive, that means that you have a damped spring. But at the same time, C, what is known as the spring constant, the coefficient on displacement, that also needs to be strictly positive. So B needs to be greater than or equal to 0, and C needs to be strictly greater than 0, both of those requirements holding at the same time in order for a second order homogeneous differential equation with constant coefficients of this nature to be describing spring motion. Make sure to check out the description part of this video down below in order to see the timestamps of the exact practice exam and question numbers that are going to be walked through as we look at all of the questions that talk about second order homogeneous differential equations with constant coefficients and discuss each of these solutions. So that maybe if you're planning on sitting down and taking one of the practice exams, you don't look at the solution to that particular question before you've done so. And as always, if you have any questions, please don't hesitate to ask. We begin with a question that has a pretty straightforward part A. We want to find the general solution of the following differential equation, y double prime plus 2y prime minus 3y equals 0. We know that this is going to rely on the characteristic equation, which looks like so. And we solve this characteristic equation in order to find its roots. We find them to be -3 and +1. And so we have two real roots. Now, the general solution to a differential equation with two real roots is going to be c1 times e to the first root times t plus c2 times e to the second root times t. And so our general solution looks like this. Part B is a follow-up question to this. It says, which one of the following is a solution of y double prime plus 2y prime minus 3y equals 4 times e to the 2t? This is a question that can be a little bit tricky. Note that what we were solving up here was equal to 0. Now we want this differential equation to be equal to 4 times e to the 2t. The way for us to do this is really just to guess and check. For each of these functions, y equals 4 times e to the negative t, y equals 4/5 times e to the 2t, y equals 4 times sine 2t, we want to separately calculate y double prime plus 2y prime minus 3y. And we want to see for each 1, 2, or 3, which one of these is that equal to 4 times e to the 2t? Well, let's take a look at option 1. With option 1, we take a moment and we calculate y prime and we calculate y double prime. And if this was our y prime and y double prime, then y double prime plus 2y prime minus 3y is going to equal -16e to the negative t, not 4 times e to the 2t. So this particular choice for y is not a solution. We have to keep hunting. We go ahead and for this particular choice of y, calculate y prime and y double prime. If these are our y prime and y double prime, then y double prime plus 2y prime minus 3y gives us, voila, 4 times e to the 2t. Fantastic. That means that this choice of y is indeed a solution to the differential equation. We can circle it and move on, but you're welcome to go ahead and try out number 3 on your own to see that it does not, unfortunately, constitute a solution to this particular differential equation. Now, do you really even need to do the work to even check this? We know that if y is some trigonometric function, sine, then y prime is going to involve cosine and y double prime is going to involve negative sine, and there's just no way that a sum of the second derivative and the first derivative and the function itself, regardless if there are actually negative coefficients on it, doesn't matter. It's not going to suddenly add up to an exponential function. There's no way that given this differential equation, this could be the solution. It just isn't related to what's on the right-hand side of this differential equation. So 2 is our answer, and we move on. Now part C is a little challenging at first because it doesn't look exactly like anything we've seen before, but we do have all the skills to solve it. It says use the substitution u equals y minus your answer to part B to find the general solution of y double prime plus 2y prime minus 3y equals 4 times e to the 2t. Well, that means that u is going to equal the following. That much we can get. Now the question is, how do we use substitution again? Substitution really is no different as a vehicle, whether you're doing U substitution or trigonometric substitution or this type of substitution. It's an algebraic rearranging of a rather tricky equation, in this case a differential equation, in order for us to get to a differential equation that is much easier to solve. So what we're going to do is we're going to take this differential equation and express it in terms of u instead of in terms of y. Well, that means that we need to get y, y prime, and y double prime all in terms of this new u. So the first thing we want to do is solve for y from this. Once we have that, we can just differentiate with respect to t to find y prime. And once more to find y double prime. Now that we have y, y prime, and y double prime all in terms of u, now let's plug all of these guys into this differential equation. Now, there's a lot going on in this. There's a ton of exponential functions that all need to be algebraically combined, so let's do that in the next line. Now, this is great because by subtracting this term onto the other side, we're left with u double prime plus 2u prime minus 3u equals 0. Substitution at work, right? We took this particular substitution, wrote our original differential equation in terms of that substitution, and it became a differential equation that we could solve. This is the differential equation that we solved. Granted, everywhere you see a u, we actually saw y in part A, but it is the one that we found the general solution for in part A. So we know what u looks like. Here's the general solution for u. But be careful, we're not entirely finished because this was not a differential equation that was asking us to solve for u. It was a differential equation whose solution was named y. And so we want to take our original substitution choice. Note that we can use either this line or this line right here to find the y that we want. And so y's solution is simply going to be the general solution we found for u plus 4/5 times e to the 2t. And we're done. Our next problem has a pretty typical setup. We're told that x of t is a function that gives the position of a mass at the end of a spring at time t, so we know that a second-order differential equation is coming our way. The x-axis is set up as shown in the diagram. X equals 0 represents the equilibrium position of the spring. That is, if the spring were resting, no one's touching it, it's at its natural length, the mass would be at 0. Note that negative values are to the left, positive values are to the right. We stretch the spring by pulling the mass out 2 units to the right. And so that x of 0, right, the position of the mass at time 0 equals 2. We let the mass go, giving it no initial velocity. Suppose that x, the position function, satisfies this differential equation. And we're told that we want to find x of t, the position of the mass at time t. All right, we begin with our differential equation, and from that we jump right to the characteristic equation, whose roots we need to solve in order to understand exactly what the general solution to this differential equation looks like. We see, or maybe we don't see, but I can see that this is going to be an upward-facing parabola that has a y-intercept at 2, which means that it has no real roots, right? So we're going to have a complex situation. We want to use the quadratic formula negative b plus or minus the square root of b squared minus 4ac all over 2a to find what these roots are. We find that this is what we get once we reduce everything almost all the way down. This term right here, the square root of negative 4, is the same thing as the square root of 4 times the square root of negative 1. Well, the square root of 4 is just 2, and the square root of negative 1 is I, so we can rewrite this as follows. Noting that every single term has a common factor of 2, we can fully reduce this to being equal to negative 1 plus or minus I. Now, remind ourselves that when we're looking at a characteristic equation that has two complex roots are going to have a real part. For us, that's the negative 1 part, and then the imaginary part, that's the plus or minus I part. And the coefficient on the imaginary part we care about, right? We have alpha plus or minus I beta. For us, alpha is equal to negative 1, and beta is equal to positive 1. That means that we can leap to the general solution for a differential equation that has two complex roots in its characteristic equation. Let's take a look at what that looks like. Plugging in our alpha and our beta, given the complex roots that we got, we have the following. This is our general solution, but we want our particular solution. How do we know, given that the question didn't say, hey, we want a particular solution, how do we know that we can get to a particular solution? Well, the fact of the matter is that not only were we given the differential equation that governs the motion of this spring, but we were also given the spring's initial position and the spring's initial velocity. So we should have no constants left unsolved for. We should be able to solve explicitly for the specific function x that gives this spring's position at time t. The first thing we need to do is consider this initial condition, that the position at time t equals 0 is 2. Well, if we plug in 0 for t and set this whole thing equal to 2, what condition will that require of our two constants? Note that plugging in 0 for t is going to make sine t go to 0, so this whole term goes away. Plugging in 0 for t will make this term 1. Plugging in 0 for d will make this term 1. So all we have left is c1 all by itself. And knowing that this has to be equal to 2 means that c1 itself is going to be equal to 2. Well, that's a relief. Now let's move on to the fact that it has no initial velocity. That means x prime of 0 is equal to 0. We need to take our general solution, find its derivative, which would be our x prime, plug in 0 for t, and set it equal to 0. We know that c1 has to be 2. What does c2 have to be in order for this to hold? All right, so when we take the derivative of x with respect to t, sorry this is a little cramped here, we have negative e to the negative t times 2 cosine t plus c2 sine t. Remember, we'd already solved for c1. Plus e to the negative t times negative 2 sine t plus c2 cosine t. This is a nice example of the product rule. Knowing that when we evaluate this at t equals 0, it has to equal 0, almost everything disappears when we evaluate at 0. Remember that anytime you see sine t, it'll become 0. Anytime you see cosine t, it'll become 1. Anytime you see e to the t, it'll become 1. So here we have negative 1 because we had a negative e to the negative t out there in front. What's inside the parentheses becomes 2. This becomes 1. What's inside the parentheses here is going to become c2. And so we're left with the fact that negative 2 plus c2 equals 0. So that means that c2 is also equal to 2. Our final answer is therefore going to be the particular solution as follows, where we plug in the two constants c1 and c2 that we have solved for into our general solution, which I guess its most updated form was right here. E to the negative t times 2 cosine t plus 2 sine t. Part B of this question asks us to determine the first two times at which the mass crosses the equilibrium position. Now, the important part here is to realize what we've solved for in part A. In part A, we found x of t, the position of the mass at time t, because position is a function of time when we're talking about motion here. And when we're asked to determine the first two times at which the mass crosses the equilibrium position, we can see that way back here in the original statement of the problem, we're told that if the spring is resting at its natural length, the mass would be at x equals 0. So when we finally get down to part B and it's asking us to determine the first two times at which the mass crosses the equilibrium position, it's asking us when we're back at that position 0. For which times t are we at position 0? So we're taking what we solved for in part A, this x of t up here, and asking ourselves, what are the first two time values such that x will be equal to 0? It's just simple algebra once you understand what the question's asking. So the major significance in this question is understanding what did you find in part A and what does it mean? Its position as a function of time, and so it's asking us for what two time values after 0 is the position going to be equal to 0. Let's go ahead and solve that. Here's the condition we're asking about. We want to know what does t have to be equal to in order for this to be true. Well, this is a product of two separate functions, e to the negative t and 2 cosine t plus 2 sine t. E to the negative t, that will never be 0. And since the product of these two things has to be equal to 0, that means our question has now simplified itself into wondering when is 2 cosine t plus 2 sine t going to be equal to 0, the first two t values for that to happen. The rest follows with some algebra and then some trigonometry. Let's take a look. We finally get down to this moment, that cosine t has to be equal to negative sine t. And if we recall our unit circle, the two t values greater than 0 when this happens are going to be 3 pi over 4. That's in the second quadrant if you're imagining the unit circle. And then 7 pi over 4. That's in the fourth quadrant if you're imagining the unit circle. I've drawn them here. Those are our two answers. T equals 3 pi over 4, t equals 7 pi over 4. All right, moving on to part C. It says at time t equals 1, determine the following. Is the spring compressed or stretched? All right, let's see what we have to work with here. Well, compression means that it's compressed, and stretched out means that it's stretched out. If we look up here at the original drawing, we see that compression corresponds to negative position values, and being stretched out corresponds to positive position values. So the question now becomes, when we look again at part C, at time t equals 1, determine the following. Is the spring compressed or stretched? Well, that's asking us, is the x value that describes position, is that going to be positive, as in it is stretched out, or negative, as in it is compressed? How do we figure that out? Well, we solved for x in part A, right? This was our x, position as a function of time, and we're just being asked, hey, at time t equals 1, is this a positive number or a negative number? Let's find out. Let's plug in 1 and see what we get. Now, a lot of students might freak out at this moment because they're like, well, I don't know what cosine 1 is or what sine 1 is or what e to the negative 1 is, but you just need to calm down and bear with us for a moment. We don't really need to know exactly what the value is. We just need to know positive or negative, and that's it, right? We want to know, okay, e to the negative 1, that's 1 over e. E is a positive number, 1 over e is going to be a positive number. Okay, that term is positive. Now, 2 times cosine 1 plus 2 times sine 1. Well, where is 1 around the unit circle? Well, we know pi is right here. We know that pi over 2, which is a little bit more than 1.5, is right here. So we know that 1 is going to be somewhere in the first quadrant where both cosine and sine are positive. So this sum right here is going to be positive as well, which means that e to the negative 1 times 2 cosine 1 plus 2 sine 1, that is going to be a positive number. All right? And since it's positive, that means that the spring, according to the picture up top again, that spring is going to be stretched out. final part of the question, it says, is the direction of motion to the right or to the left? Well, direction of motion, moving leftwards, rightwards. X only tells us position. It doesn't tell us where we're headed. But velocity, x prime, that would tell us the direction that we're headed, right? If we go back up to this top picture here, we see that we have a spring, mass at the end of the spring. If its velocity is positive, that means x is increasing. That means x is moving to the right. If velocity is negative, that means x is decreasing. That means x is moving to the left. So what this question is really asking us down here when it says, is the direction of motion to the right or to the left? It's asking whether x prime at t equals 1 is positive or negative. So this question here, C, is a really rich question because it's really testing whether you understand the functions that you've spent time solving for in part A. We had to go through both a general solution as well as a particular solution. And once you have that particular solution, all the different things that it can tell you about what's happening at a particular moment in time. So let's get to it. We want to figure out if x prime evaluated at 1 is going to be positive or negative. Now, the first thing I want to say is that there's a little bit of a common sense shortcut to avoid a ton of computation. Obviously, the way we approached part 1 of this question works in part 2. If you calculate x prime from our particular solution and you plug in 1, you will find that it's less than 0. So that means that the spring is moving to the left, or the mass on the edge of the spring is moving to the left. But there's a quicker way to do this. We know that at time t equals 1, the spring is stretched out. And what's key about that is, if you recall the initial conditions here, we know that at time t equals 0, it is stretched out to 2. So we know that at time t equals 1, it's still stretched out. We know that there's no initial velocity, so this mass is stretched out and then released, right? It's pulled out here and then let go, and it's going like this. But what's happening, what's interesting, is that from our work in part B, when we found that the first 2 times at which the mass crosses the equilibrium point, we found that the first time was 3 pi over 4. Now 3 pi over 4 is over here. The value 1 is somewhere over here. So note that we started stretched out at a displacement of positive 2. We released it. There was no velocity. If we release it, the spring is moving to the left. It's moving to a compressed position, and then it'll move to being stretched out again, then move to being compressed again. But the key thing here is that we started stretched out, we released it, it passes through the equilibrium position at t equals 3 pi over 4. T equals 1 is before that happens. So we're going from stretched out to equilibrium position. It's going to bypass the equilibrium position and go to a compressed place as it oscillates back and forth. But the key notion is that we started stretched out and we're headed to an equilibrium position, and t equals 1 is somewhere in here. So it's moving to the left during this process as we go from stretched out to equilibrium position. So this is movement to the left. Now, of course, what's interesting is that you could have done it the same old way that we did part 1, as I said, where you computed x prime, evaluated at 1, and found that it was less than 0. And that is totally doable. It takes a little bit of algebra, very similar to part 1 up here, but it works just as well. Either one would net you full credit. Let's take a look at our next question. Our first is asking us to consider the following 4 differential equations. They're all second-order homogeneous differential equations with constant coefficients. And we're asked for which of the differential equations above is the limit as t goes to infinity 0 for the solution y. And that says regardless of the initial conditions. So we basically need to figure out what these solutions look like for each of these, write them down, and see if we can figure out whether the limit behavior as t grows without bound is 0, no matter what the constants happen to be. Let's take a look. Let's start with number 1. What you want to do with 1, 2, 3, and 4 is find the roots of the characteristic equation and then put those into the general solution for a second order differential equation with constant coefficients with a characteristic equation and roots of that type. All right, beginning with our very first differential equation, we find that the characteristic equation is r squared minus 4r plus 3 equals 0. The roots are two real roots. They're 3 and 1, which means that our general solution is going to look like some what we call linear combination, c1 e to the 3t plus c2 e to the t. Now, regardless of what c1 and c2 are, as t grows without bound, these terms will grow without bound in terms of magnitude. And so there's just absolutely no way that, given that c1 and c2 are just constants, that y of t is going to somehow be equal to 0 in the limit. So 1 is unfortunately disqualified. Both of these will either grow without bound in terms of magnitude, maybe positive infinity, maybe negative infinity, but one or the other. Let's take a look at possibility 2. Now, on the other hand, possibility 2 is pretty fantastic. This ends up being an easily factorable characteristic equation, two real roots. They're -3 and -1 though. So the general solution is going to be c1 times e to the -3t plus c2 times e to the -t. And both e to the -3t and e to the -t, those are both going to shrink down to 0 as t grows without bound, regardless of what c1 and c2 are. So here we have our first contender. That is that differential equation 2 right up here is the first equation whose solution is going to be equal to 0 as t goes to infinity, regardless of its initial conditions. So 2 is one of our choices. Let's take a look at 3. Option 3, a little bit more challenging. We find that this characteristic equation actually has two complex roots. It's going to be -1/2 plus or minus I times the square root of 11 over 2. Now, what's interesting about this, however, is when we put that into the appropriate general solution format for a differential equation like this, we end up with e to the -t over 2 times c1 cosine square root of 11 over 2t plus c2 times sine of square root of 11 over 2t. This gobbledygook in here does not matter so much. It is periodic if it's totally left alone, but the issue is this coefficient out here. This will cycle again and again and again forever, but its amplitude is basically being controlled by this function, e to the -t over 2. And as t grows without bound, this is going to go to 0. So number 3 is another differential equation whose solution is going to go to 0 regardless of the initial conditions. The initial conditions are just going to tell us what c1 and c2 are. It's not going to change the limiting behavior. What's controlling the limiting behavior is actually what's out here, that e to the -t over 2. So 3, this is definitely one of our options. Last but not least, option 4. Let's investigate. Now, 4's characteristic equation is pretty easy to solve. We find that r squared has to be equal to -3, which means that r is equal to plus or minus the square root of 3 times I. Well, we need to interpret this as a complex number right here. And we note that the real part, the alpha part, that's 0. The beta part is root 3. So when we put that into the general solution, we find that we have e to the 0 times t, which is 0. And so this term out here is actually equal to 1. Times c1 cosine of root 3t plus c2 times sine of root 3 times t. And so this part right here, this is periodic. It's just getting multiplied by 1 because no longer is this limiting behavior controlling the limiting behavior of the entire function. This is just going to be periodic. It's going to coast, depending on what c1 and c2 are, between peaks and valleys for the remainder of all time, really, as t goes to infinity. So this does not have a limit value of 0 as t goes to infinity. So our two winners are equation 2 and equation 3. We're then asked in a quick follow-up, which of the differential equations above could model a spring in a frictionless system? And of course, because we're expert about second-order differential equations that are homogeneous with constant coefficients, And specifically, we know that in order for spring motion to be modeled by a second order differential equation, we need that constant on y prime to be greater than or equal to 0, and the constant on y to be strictly greater than 0. Now that constant on y has to be positive because that's the spring constant. That's that feeling that you get when you pull out a spring and it's pulling away from you, and you push in a spring and it's pushing against you. That's what that is. But that coefficient on y prime, that's what indicates friction. So if we're going to be in a frictionless system, the coefficient on y prime has to be 0. Friction cannot come into play. And so if we're looking at one of these, which of the differential equations above could model a spring in a frictionless system? Well, 1, disqualified, negative coefficient on y prime. 2, disqualified, positive coefficient on y prime. 3, disqualified, positive coefficient on y prime. 4, works for me, coefficient of 0 on y prime, but also positive coefficient on y. So option 4 is the only one that could possibly work here. Now in our final problem, which I'm not going to scroll too far down to work with because we really want to keep all our work from A still viewable, which of the differential equations above has a solution or solutions which are periodic with period 4 pi over root 11? List all. Well, we have all our general solutions worked out from before. And we see right off the bat that option 1 and option 2, not periodic at all, right? Periodic means that the function exactly repeats itself again and again and again. Like you could highlight and like copy paste over and over and over again to reconstruct the entire function. Now we're left with 2 possible options, 3 and 4. And we remind ourselves that the coefficient on t inside the trigonometric function is what makes adjustments to a function's period. And so the one that has the appropriate adjustment, that would be taking the period and creating a period of 4 pi over root 11, would be something that's going on in option 3. Am I correct? Yes, I'm correct. However, is option 3, this general solution, actually a periodic function? Well, I mean, this part is periodic, but the problem is that it's not just this part alone. You also have to take this part into account as well. That e to the negative t over 2 is making the amplitude decrease with every passing oscillation. So while this function is oscillating, as in it increases and it decreases, then it increases and then it decreases, it is not periodic because its peaks are getting shorter and shorter and shorter. Its valleys are getting shallower and shallower and shallower as you go on. It is not a copy-paste situation where it exactly repeats itself for the rest of time. So unfortunately, none of these are periodic with period 4 pi over root 11. This one is periodic, but its period is not 4 pi over root 11. We're forging onwards. Here we go. We modeled the motion of a vibrating spring because why wouldn't you? With the differential equation of x double prime plus 2x prime plus 5x equals 0, where x gives the position of the spring at time t. As always, initial conditions are that at t equals 0, x is equal to 0, and at t equals 0, x prime, is equal to 2. All right, it first says find the general solution to the differential equation. Awesome. We want to take the characteristic equation, find its roots, and select the appropriate general solution format to plug them in. We find that the roots are -1 plus or minus 2i, so our alpha is -1, our beta is 2. We put that into our general solution that's given to us by taking our regular general solution as if we had 2 real roots and applying Euler's formula to it. But anyway, that is e to the negative t times c1 times cosine of 2t plus c2 times sine of 2t. We're then asked to interpret the initial conditions that x of 0 is equal to 0 and x prime of 0 is equal to 2 in words. Give a sentence in English describing the initial conditions in terms of the spring system. This is checking whether you understand the physical significance of these conditions. Remember that x gives position at time t. X of 0 equals 0 means that at t equals 0, the spring is at its equilibrium position. The fact that its derivative at t equals 0 is 2 means that at t equals 0, well, the derivative of position is velocity, and 2 means that it is moving to the right usually, or towards being more stretched out. So x is increasing. I think that saying moving to the right or stretching out at a rate of 2 units per second, either one would be fine. And part C says find the particular solution given by the initial conditions. So we're basically applying these two initial conditions that we have here to our general solution to solve for C1 and C2. Let's take a look at what we get. The first one is to say that, okay, when we evaluate this at 0, we should get 0. Well, when we evaluate this at 0, this entire first term here becomes 1. Cosine of 2t becomes 1, so we have C1 left here. Sine of 2t becomes 0, so this whole thing is eliminated. All we're left with is C1 by itself. So that means that if x at time t equals 0 is equal to 0, that means that C1 has to be equal to 0. Now let's take a look at x prime. Now what's cool about this is that the derivative is not nearly as complicated as you think, because by solving for that first coefficient, we know that C1 is equal to 0. So if we apply that to our general solution, we already know that it's at least going to look like e to the negative t, that is a negative t up there. My stylus went a little crazy. Times C2 sine 2t, because we know that C1 is equal to 0 up here. So this derivative is a lot easier to take. That leaves us with negative e to the negative t times C2 sine 2t plus e to the negative t times 2 C2 cosine 2t. Got to remember the chain rule in there. And then we want to evaluate that at 0 and make sure that it's equal to 2. Well, again, a lot of stuff is eliminated because sine 2t here when t equals 0 is 0. So C2 times it is 0. And negative e to the negative t, that whole thing, this whole term is just going to go away. So we're left with e to the negative t evaluated t equals 0. So that's 1. 2 C2 cosine 2t. Well, cosine 2t, that's going to be 1 because t is 0. So we're left with 2 times C2, and that whole thing has to equal 2, which means that C2 is equal to 1. So now that we know that C1 is 0 and C2 is 1, we're left with the fact that, all right, that means that x of t is going to be equal to e to the negative t. There's no C1 cosine 2t because C1 is 0. So times C2 sine 2t, and we know C2 to be equal to 1, so it's just e to the negative t times sine 2t. And that is it. Part D is a nice follow-up question. It says, let x be the particular solution that we found in part C. Find the limit as t goes to infinity. Well, we know that sine 2t is periodic. It's just going to oscillate forever and ever between 0 and 1, but e to the negative t. Ooh, well, as t grows without bound, that's going to go to 0, and this is controlling the amplitude. So that means that our crests get a little less crestier and our valleys get a little less vallier. So there's not, the amplitude gets smaller and smaller and smaller as we go off to infinity. It's going to look, you know, something like that. They get small. That was a terrible artistic rendering, but they get smaller is what I'm trying to say. So we know that the limit of this limit as t goes to infinity of e to the negative t times sine of 2t, that's going to be equal to 0. Now, give an interpretation in English of the result that we got in part D, explaining in terms of the spring. Okay, well, at first the spring is at its equilibrium position, but someone is sort of stretching it outwards at a rate of 2 units per second, and then they let go. And then the spring oscillates for a bit of time, right? It sort of goes back and forth, it bounces. But this is a spring with friction, and so it bounces less and less and less and less and less. And so in the limit, it's just returning to rest at its equilibrium position. I'll leave that to you to sort of put in bullet points. Here, I'll write some down. There, beautiful. As t goes to infinity, it oscillates continuously, but less over time, and then the limit returns to its equilibrium position. So not only do you need the ability to solve these differential equations, but you need to understand if they're modeling motion. What kind of motion is that? What does it look like? You can't just walk in there with a set of rules and algorithms and things you plug in, et cetera, et cetera. You've got to have a flexible understanding of the concept. All right, a familiar picture greets us with this problem. It says if b is greater than or equal to 0, the differential equation x double prime plus bx prime plus 4x equals 0 models the position x of a mass on a spring at time t. The x-axis is set up as shown in the diagram below so that x equals 0 represents the equilibrium position of the spring, and the number b describes the amount of friction. Suppose b equals 5, so that this is our differential equation. If the mass is pulled out, stretching the spring 1 unit from its equilibrium position, given an initial velocity of 2 units per second, causing it to sort of, in the aftermath of letting go, causing it to stretch out even more, find x of t. So we are given a differential equation, we're given 2 initial conditions. That means when we're looking for x of t, it's not going to be a general solution. It's going to be a particular solution. Of course, we'll have to move through the general solution to get there, so let's find that general solution first. I want to know the characteristic equation for this differential equation. I want to know its roots. All right, got them. Very nice. Roots are both real. Love those. -4 and -1. That means that its general solution is going to be equal to some constant times e to the -4t plus some constant times e to the -t. Now we use the fact that at time t equals 0, we know the spring is stretched 1 unit from its equilibrium position, so that means that at t equals 0, x is going to be equal to 1. Let's use that. And then the fact that its initial velocity, x prime, at t equals 0, is going to be equal to 2. Let's write both of those down now. The first one is easy enough to set up, right? It says that if we evaluate this at t equals 0, we should get 1. Well, evaluating both of these exponentials at t equals 0 is going to give us 1, so that leaves us with c1 plus c2 has to equal 1. Of course, knowing that the derivative at 0 is equal to 2, that's a little bit more challenging. We take the derivative with respect to t. We find this to be x prime of t. And we know that when we evaluate at 0, we should get 2, which means that -4 times c1 minus c2 should equal 2. This is pretty nice because we can actually just add these two together. We're going to get -3 c1. The c2's will cancel each other out. And then we know that that's going to be equal to 3 on the right-hand side. So that means that c1 is going to be equal to -1. And of course, if the sum of c1 and c2 is +1, if c1 is -1, then c2 must be 2. Now that we've solved for both constants, we can put them together into our particular solution. Our particular solution is going to be that x of t is equal to c1. Note that we have to keep these straight, very important. c1 is -1, so we have -e to the -4t. Plus c2, and c2 is 2, plus 2 times e to the -t. And that is our final answer for part A. Little bit of graph matching. It says which of the graphs below shows the function x that we found in A. Note that this function is exponential decay. It is not periodic. There's not a long-term oscillation. And so that is going to disqualify quite a few. It disqualifies C, it disqualifies F, it disqualifies D, it disqualifies A. All of these are definitely the graphs of particular solutions that involve trigonometric functions. We've had experience with those, right? Well, we're left with B and E. They both look like they could be exponential decay. They both have the right limit behavior. That's sort of what I always look at, where I'm like, okay. You know, what's happening as t goes to infinity? As t goes to infinity, this is going to 0. That's happening with both of them. What's the major difference? Well, yes, this one becomes negative, but the major difference is actually at the start. Note that this is immediately sloping downward. That means that x prime at 0 in part B is negative, and x prime in E at 0 is going to be positive. And of course, if we go back here and look up at the top, we see that our conditions said that x prime of 0 should have been equal to 2. It needs a positive slope, an initial positive slope. And so that means that our correct selection should be E. Exponential decay, positive function value at t equals 0, positive slope at t equals 0 if it's all of the characteristics of our particular function. This is a continuation of that problem, and it says suppose that b equals 1. So the differential equation actually looks like this, and it says which of the graphs on the previous page would be a graph of the spring's position over time. Twist. Oh my god. So we're not quite done with all those graphs from the previous page. We need to figure out exactly what the general solution looks like for this particular type of differential equation. Let's take a look at its characteristic equation. Let's find those roots. Let's figure out what the general solution should look like. All right, here's what I got. The characteristic equation, r squared plus r plus 4 equals 0, has two complex roots, -1/2 plus or minus I times root 15 over 2, which gives us a general solution which looks like this. Now the important part to note is that regardless of what C1 and C2 happen to be, this is periodic inside here, but it's being multiplied by an exponential function that is tending to 0. So that means that the entire function, when taken into account, is not periodic. It will oscillate from this sum of trigonometric functions, but the amplitude is going to decrease over time. So we're looking for an oscillating function, amplitude decreasing over time. I can't turn back given the limitations of the software, but D is the one of the graphs that actually does this. It's the only one that does this. Now, D part, it's a really juicy problem. It says in parts A and C, you looked at two different values of B, 5 and 1. And one of these values described a spring that oscillated. That was the 1, B equals 1. And it crossed the equilibrium position infinitely many times. And the other describes a spring that does not oscillate. That was when B equals 5 at the beginning of the problem. It said, what are all values of B that cause the spring to oscillate? Now note that the coefficient on X, the spring constant, is always 4 here. So what we're really asking ourselves is, how do we set this up? X double prime plus bx prime plus 4x equals 0, so that we have a situation that will cause the spring to oscillate. Well, of course, if we have two real roots to this characteristic equation, then we would just have a general solution that's a sum of exponential functions, just like we had in part A. But of course, if we have complex roots, right, if what's under the radical right here is negative, then we know we'll have oscillating functions. So it says, what are all the values of B that cause the spring to oscillate? Well, what ends up happening is we have negative B plus or minus the square root of B squared minus 4. A is always 1. C is always 4 here, all over 2 times A. Now, we don't care about this part out here, right? This part is just controlling this right here. We want to make sure of the fact that what is underneath the radical sign is going to be negative. That will trigger the general solution that involves trigonometric functions that will give us oscillation ad infinitum. Even if the limit does happen to be 0, what we mean by that is, yes, the limit is 0, but we never actually reach there. We actually just keep oscillating just tinier, 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 things like that. So we're really just looking at what's underneath the radical sign. And specifically, we need this, right, to be equal to something that's negative. It needs to be a complex number. What's underneath there, the b squared minus 16, has to be negative, which of course means that b squared has to be less than 16, which means that b has to be less than 4. And you might say, whoa, 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 that also means that b has to be greater than negative 4. And I say whoa to that as well, because we're talking about springs here. So b has to be at least greater than 0 in order to describe a spring that oscillates. So b has to be less than 4 in order to trigger these complex roots that will create the need for a general solution that involves oscillating functions, but also b has to be greater than 0, greater than or equal to 0, I should say, in order for it to even model spring motion. So our final answer is going to be that 0, b has to be greater than or equal to 0, and less than 4. That looks kind of like a 9. I apologize. 4. There we go. And E, to me, ironically, now that we've sort of delved so deeply in part D, E is a little bit lighter of a question. It says if the spring had no friction at all, that means B equals 0. Which of the graphs above would be a graph of the spring's position over time? Well, the differential equation would then be x double prime plus 4x equals 0. Our characteristic equation would be r squared plus 4 equals 0, which means that r would be equal to plus or minus 2i, right? Because when you square 2i, you're going to get negative 4. And so what does that give us? Well, that means that alpha, the real part of our complex number, is 0, and beta, the coefficient on the imaginary part, is 2. So our general solution looks something like this. And you might say, hey, what happened to e to the alpha t? And I remind you that alpha is equal to 0, so e to the 0 times t is e to the 0, which is just 1. So we're left with c1 times cosine 2t plus c2 times sine 2t, and you have to remind yourself, what happens to a trigonometric function when I multiply t by something inside that function? Well, when I multiply by 2, I'm multiplying the period by its reciprocal. So when I multiply t by 2, I'm making the period half as long as it used to be. So instead of a period of 2 pi, I now have a period of pi. And so I want to see peaks and valleys, I should say, of this function that are pi units apart. Again, unfortunately, I can't flip the page backwards, but if you were looking at the 6 graphs, we're looking for something that is periodic with a period of pi, and the only one that does this is F. The period is too short in C for it to be the correct graph. So that was a pretty fun one. It started off kind of entry level, find your general solution, particular solution, but then you had to really get into, okay, under what conditions am I going to trigger complex roots so that I involve an oscillating function? That was pretty fun in D. And I think this one is a good example of the fact that even if you couldn't understand D, you could certainly, E had no bearing on that. So if you get stuck on a part on the exam, move on to the next part, see if it's something that maybe you can suss out anyway. All right, there are only so many physical situations where springs actually come in handy, but here we have the chefs in Oliver's restaurant. They keep leaving the swinging door to his kitchen open, so he installs a rusty spring with lots of friction to make the door close after someone lets it go. So you'll make use of the following images as you solve the various parts of this problem. And already, with all of our experience with second-order homogeneous differential equations with constant coefficients, we can see that this is all going to come down to, can we find the general solution? Is it going to be something with real roots where we have exponential decay, or is it going to be something with complex roots where there's some oscillating behavior? All right, it says, suppose the position of the spring satisfies the equation that's given here. And it says, find the general solution of the differential equation. So find that characteristic equation, find those roots, and then based off of the roots, plug them into what you know the form of the general solution should be there. This is not too bad. The characteristic equation ends up being really nice to factor. It has 2 real roots. And so we have x of t is equal to c1 times e to the negative 5t plus c2 times e to the negative 2t. Now, just as we have this sneaking suspicion of what's about to happen, it says Oliver holds the door open so that the spring is stretched to the length of 4. So it's stretched out 4 units. That's its position at t equals 0. It says, which of the graphs above best represents the position x of the spring t seconds after Oliver releases it? Write the correct letter in a box and give 1 sentence of explanation. All right, well, let's take a look up here. We know that our general solution is going to be some sort of exponential decay. That doesn't change based on the initial condition. So based on what the general solution looks like, it's impossible for the door's motion, or spring motion, I should say, to be modeled by A, which oscillates, or B, which oscillates, because this does not oscillate. So we're left with C and D, which both exhibit exponential decay. And when we're told, hey, when he stretches the door open at time t equals 0, the spring is stretched to a length of 4, that means that x of 0, right, is going to be equal to 4. The only one between C and D which have a value of 4 at t equals 0 is going to be D. So D is our answer here. And I'd expect a sentence of explanation that involved exponential decay and the fact that the initial function value has to be 4. Woohoo! Moving right along. Okay, well, Oliver is super picky. He decides that the door closes way too slowly, and he decides to oil the spring in the door, and the new equation for the spring position is the following. We're told that, okay, it's x double prime plus 2x prime plus 10x. Note that the spring constant itself has stayed the same, that 10. But unfortunately, you know, the coefficient now on x prime is different. Why does it make sense that the coefficient of x prime is now smaller? A brief sentence will suffice. Well, the coefficient on x prime indicates the amount of friction on the spring. So before, when he says that the door closes too slowly, that means that friction is too great. So in order to decrease friction, you need to decrease the coefficient on x prime. That would be my brief sentence. Now it asks us to find the specific solution of that new differential equation that satisfies the initial conditions that he's opened the door 4 units at t equals 0, and it is technically, well, he's just releasing it. It's sort of like at rest, and then he releases it. He's not throwing it open. He's not slamming it closed. Its initial velocity is going to be 0. Don't jump to the end. The first thing you want is that characteristic equation. Solve for its roots. Find the general solution. All right, here's the characteristic equation. Solve for the roots. They're -1 plus or minus 3i. So that leaves us with the fact that our general solution should be of the form e to the negative t times c1 cosine 3t plus c2 sine 3t. Now we've got to use those initial conditions to figure out what c1 and c2 are equal to. The fact that when x is evaluated at t equals 0 should give 4 means that c1 has to equal 4, because basically this goes to 1, this totally disappears because sine of 3 times 0 is 0, and so you're left with the fact that c1 has to be 4. The second part, that x prime of 0 has to be 0, that's a little trickier because we need to solve for what x prime is. Now, finding that x prime here has to be equal to 0 when evaluated 0 means that e to the 0, negative e to the 0, that's -1 out front. The only term that remains in here, this goes away. We have c1 cosine times 3t. We know c1 to be 4 already, so that's 4. This becomes 1. This goes to 0. This becomes 1, so we're left with 3c2. -4 plus 3c2 somehow equal to 0, only if c2 is equal to 4/3. So once we have both those facts, we know for a fact that our particular solution, x of t, is going to be equal to e to the negative t times c1, which we found to be 4 cosine 3t, plus c2, which we found to be 4/3 sine 3t. And that is what we've been able to solve for. That's our particular solution. Now it says, for your specific solution above, which of the graphs above now best represents the position x of the spring t seconds after Oliver releases it? Write the correct letter in a box, give one sentence of explanation. Well, of course, now we're looking for something that oscillates, but we're also looking for something that the amplitude gets smaller and smaller as t goes to infinity. Unfortunately, that's going to disqualify the two exponential decay functions, c and d. But between a and b, they both oscillate and the amplitude is decreasing. But the big difference between the two is that while the function value is positive for both a and b, the first derivative of the function value, x prime, is negative for a and it's 0 for b. And we remind ourselves that we wanted our x prime to be equal to 0. And so when we take a look at that, that means that b is going to be our answer. Not only does it oscillate, it oscillates with decreasing amplitude. Has an initial function value, x of 0 equals 4, and x prime of 0 equals 0. And that's it. Woohoo! All right, here's another problem. If you've been going through this video with me just on repeat, you should be like, oh, okay, here we go. Another mass on the end of a spring. We have a differential equation here that models the position of this mass on a spring. Note that the x-axis is set up so that 0 is the equilibrium position. Positive means it's stretched out. Negative means that it's compressed. First question is, what is the general solution of this differential equation? Well, that means that we need to find the characteristic equation, find its roots. 2 real roots, one of them in -3, one of them in -2. Whew, my goodness. That means that our general solution is going to be a sum of exponential functions that looks like this. Moving right along, it says if the mass is pulled to the right, stretching the spring 2 units from its equilibrium position, and the mass is given an initial velocity of 3 units per second to the right, find x of t. Note that moving to the right is increasing x, so that means that velocity is going to be positive. So that means that we have 2 initial conditions, one of which is that x evaluated at 0 is equal to 2, and then that initial velocity, x prime evaluated at 0, is equal to 3. We're going to plug in both of these initial conditions into our general solution and try and solve for C1 and C2. Now, of course, we had to do a little bit of finagling to find what x prime of 2 even looks like. Now, x prime evaluated 0 is -3c1 minus 2c2. Not exactly the most cooperative system of equations I'd ever seen before in my life, but it's really not so bad. Let's multiply that first line up here by 2, and then we'll add it to the second line. In the blink of an eye, we've solved for one of the constants. And then the fact that C1 plus C2 have to equal 2, that means that C2 is going to have to be equal to +9. What else is there? Well, we need to find x of t, so let's write that out. We have our C1 and C2 now. We have x of t is equal to -7. We have to be really careful that we're actually making sure we're plugging in the right C1, which is the coefficient on e to the -3t, and then +9 times e to the -2t. So that's our first little bit of solution. And then it says to draw a very careful sketch of x versus t. I love that it says, did you draw a careful sketch? Well, what does it mean by careful? Well, we know we need exponential decay involved because we know as t goes to infinity, this is going to go to 0. The other thing that we know is that its initial position has to be 2. I'm going to label that, right? We got that from this fact right here. Then we also know that the initial velocity has to be 3. So right off the bat, we're first going to increase and then we're going to decrease all the way down to 0. So careful sketch there. Not gonna lie, that was a little bit ugly. But what are we looking for in a careful sketch? The right initial function value is 1. The right increase or decrease at 0, right? Slope of the tangent line, what that derivative should be. The sign of the derivative should be apparent. And then the correct shape. This is not a periodic function that goes like this. It is an exponential decay function. And of course it says, please indicate which of the following are true and which are false by circling the correct choice. No explanation is needed. All right. The first statement is the model above models a spring system with friction. Well, let's take a look here. All right, the coefficient on x is strictly positive. Great. The coefficient on x prime, greater than 0. Yes, has friction. I agree with that. True. For just the right initial conditions, the solution of the system above could be the plot to the right. Now this plot to the right here, very different from our exponential decay. This has sine and cosine involved. We remind ourselves that sine and cosine only get involved when we have complex roots of the characteristic equation. Okay. And this is saying that if we just had different initial conditions, maybe we could end up with complex roots that would require this kind of function. That's false. The initial conditions don't ever affect the general solution. The initial conditions allow you to find a particular solution, but the roots of the characteristic equation, which come directly from the differential equation, those are what decide what your general solution looks like. And so under these conditions, with this particular differential equation, we're always going to have exponential decay. Changing the initial conditions may change, for instance, whether there's a positive slope or a negative slope or zero slope or what the actual initial value is for the function, but it's always going to have a similar shape that obeys the fact that it's going to be some constant times e to the negative 3t plus another constant times e to the negative 2t. It's always going to be an exponential decay. It's never going to spontaneously turn into this type of function that oscillates just by changing the initial conditions. The initial conditions only allow you to solve for C, C1, C2, whatever that happens to be. They don't allow you to change the general solution for the function. So that's a false answer. Next comment is, no matter what the initial conditions for the spring described above, the mass will always be furthest from the equilibrium position at t equals 0. And we can just look at this picture right here to see that that's false. That's not true. Note that our initial condition in this particular action with the mass, we grabbed it, we stretched it out, and we sort of flung it outwards. So even though it was at 2 at t equals 0, position 2 at t equals 0, it still traveled away from the equilibrium position, sort of maxed out here at some time stamp that's not t equals 0 before it returned to the equilibrium position. So this is not true. We actually have an example right here. And so this true or false question is really seeing whether you understand the physical significance of the solution that you found and that you've graphed correctly. So this is going to be false. And that's that. And now for our final question in this family of questions about the topic of second order differential equations. Homogeneous differential equations with constant coefficients. All right, it says the planetary lander has a shock absorbing spring built into its landing gear, and the engineers have designed the spring chamber so that the compression x of t of the spring obeys the following differential equation. We're given this second order homogeneous differential equation with constant coefficients. We're asked to find the general solution of the given differential equation. So that means, what is its characteristic equation? What are its roots? Put them into the general solution. We find that the roots are both real, -1 and -3, and we plug them in. C1 times e to the negative t plus C2 times e to the negative 3t. All right, it says that when it lands on the planet's surface at time t equals 0, the shocks are not compressed at all. So all the springs are at rest. X of 0 equals 0, and the lander is traveling with velocity x prime of 0 equals -10. So we're given these two initial conditions. We want to find the particular solution of the differential equation that satisfies these. So let's plug those in and see what C1 and C2 have to be in order for these two initial conditions to hold. All right, we do have to do a little bit of additional computation for that derivative initial condition, but at least the first one's really nice. Evaluating x, our general solution here, at t equals 0 makes both of the exponential functions go to 1. So we have C1 plus C2 equals 0 in order for that condition to hold, in order for x0 to be 0. For x prime of 0, we need to figure out what x prime is in general. Little chain rule action, right? Negative C1 e to the negative t minus 3 C2 e to the negative 3t is what we have. Plugging in 0 for t, those exponential functions will go to 1. And we're left with negative C1 minus 3C2 is equal to -10. All right, well, adding those two things together, the C1s will drop out, and the C2, we are left with something. We have that negative 2C2 is equal to -10, which means that C2 is equal to 5, which means that C1, given that first equation right here, how useful, C1 will be equal to -5, given that C2 is equal to +5. This means that our particular solution is going to be x of t, which is equal to -5 e to the negative t plus +5 e to the negative 3t. Woohoo! If you've been through the rest of this video, you probably feel like a total pro by now. All right, let's see. Which of the following could be a plot for our solution to part B? Please circle one. No explanation is necessary. I'm going to explain it whether you like it or not. I hope that's why you're watching the video, though. So this should be some sort of exponential function. It does not oscillate, which means that right off the bat we can say no to 1 and no to 3. We're left with 2 and 4 that both have the appropriate limit behavior that this function is going to 0 as t is going to infinity. And of course the difference here, both of these have the correct first derivative, negative, right? But their initial function is different. This one has a positive initial function value. This has a 0 initial function value. Which one did we care about? Scrolling up to take a look back here, we wanted the initial function value to be 0. And so that leaves us with the fact that the one that we really like here is going to be 2. Right there. No explanation necessary, but I gave it to you anyway. And of course, your ability to understand graphics, very important. Let's take a look. The plot on the right is a particular solution of a second order differential equation of the following form, with initial conditions where x is equal to something when t is 0 and x prime of 0. And the question is, what can you say about whether each of the following quantities must be positive, negative, or 0? Please circle the appropriate choice for each quantity and no explanation is necessary. Well, the first thing that we want to take a look at with this function is that it is oscillating, but its amplitude is actually increasing. So that's rather bizarre. This is definitely not a spring in any sort of world that I'm aware of. So that's the first thing that is a little bit strange. The easier parts of this problem are actually down here, right? b squared minus 4c, that is pretty challenging, but x evaluated t equals 0, x prime evaluated t equals 0, not so bad. So let's take a look. X evaluated at t equals 0, that is, what is the function value when t equals 0? Well, the function value here is negative down there, right? It's below the t-axis, so that's the first thing that we can definitely say. And x prime of 0, it looks positive to me. Definitely doesn't look like it's happening quite at a valley yet. So I'm looking down at this area. What is the slope right there? Looks positive. Now the next question is, how the heck do you even get a second order differential equation like this whose particular solution appears like this? And of course, it's not going to happen if you have one repeated root. It's not going to happen if you have two real roots. It's definitely going to happen if you have imaginary roots. So let's remind ourselves of what those imaginary roots come from. They come from the characteristic equation, right, that looks like this, whose roots are found in this way. The one thing we do know is that a, I guess, that's, the quadratic equation. A is 1 here. We don't know what b is. We don't know what c is. We know that a is 1. And so when we get to trying to figure out what the roots are, we end up looking at the following. Now, here's what this looks like split up. And I did this because in order for us to involve sine and cosine, some sort of oscillating function in the general solution, we need to have complex roots. We need to have negative b over 2, that becomes alpha. And then this whole thing becomes I beta. And that only happens when b squared minus 4c is negative, right? Because that's where the I comes from. So the first thing that we do know is that in order for the oscillating to happen, we need to have complex roots. And in order for us to have complex roots, what's under here has to be negative. So we know that b squared minus 4c has to be negative. Amazing. That's another thing that we know. Whew, okay. Well, the other thing that's interesting is that when it asks about c, it says, does it need to be positive, negative, 0? Not enough information. Well, we know that what's under here has to be negative. b squared minus 4c has to be negative. Okay. And b squared is always going to be 0 or positive. So c definitely can't be negative because then minus 4c would be adding on to that. And we wouldn't have an imaginary number. We wouldn't get a negative under that square root sign. So knowing that b squared is at least 0, right? That means that c has to be positive. If c were 0, what's underneath the radical sign would be 0 or greater. If c is negative, what's underneath the radical sign is definitely going to be greater than 0. So c has to be positive. And then last but not least, I think the most challenging question is, what's the deal with b? Well, let's take a look at B here. B is really the only thing that affects alpha. And we see that the amplitude here is increasing. And so when we take these complex roots and we actually put them in the general solution, right, we get e to the alpha t times c1 times cosine beta t plus c2. Honestly, don't really care about the rest of this. I really care about this guy right here. Ooh, e to the alpha t. So this term is controlling the amplitude of these otherwise totally polite periodic functions. It is making them as a whole not periodic. This is making the amplitude greater and greater and greater and greater as t goes to infinity, or smaller and smaller and smaller and smaller as t decreases in some other problems. But of course, in our problem, as t increases, the amplitude is increasing. So that means that this e to the alpha t, as t goes to infinity, it needs to be going to infinity as well. That means that alpha must be positive, which means that negative b over 2 must be positive, because that's what goes into alpha. Negative b over 2 is alpha. And so if negative b over 2 has to be positive, that means that b itself, that has to be negative. Whew, and we finished the problem. That's it. That's all of the practice exam problems involving second order homogeneous differential equations with constant coefficients. I really hope that looking at a bunch of these problems of this type have given you some new confidence and maybe some insights into exactly what you're doing, how to manage these problems, what do the functions look like, what kind of motion do they describe, how can you manipulate them accordingly, and that you feel like you walk in to our final exam hoping that a question on springs or just second order differential equations with constant coefficients shows up. As always, please don't hesitate to email or ask questions in office hours.